Morning all. Hope everyone's okay. Who have we got online today? Bet Tanisha will be one of the first people to say hello. So today we're going to start having a look at Chemistry 2. We did Chemistry 1. There you go. Morning Tanisha. Last week we did Atomic Structure. So we looked at how we can use the periodic table to identify... Morning Amy. How we can use the periodic table to try and identify atomic structure, looking at the atomic mass, looking at the atomic number. We looked at electron configurations. We started looking into ions. We went through chemical reactions to do with Group 1 and Group 7. And we're going to start expanding on that today with the next unit, which is Chemistry 2. Morning, Chris. So I'm going to start off with some of the fundamentals. As usual, this is sort of suitable for foundation and higher, although later on I'll probably go through some more advanced stuff that we need for those of you that are looking at pushing it further. But really getting the basics and the sort of foundation understanding is really, really key for this. Being able to use the periodic table properly and usefully is probably one of the most important skills, because if you can do that, then actually most of what we're going to go through today you can actually learn and pick up from inside the exam. One of the biggest areas for this, and this is a question that comes up pretty much every year, guaranteed. So when we're looking at ionic covalent, there will definitely be something in the exam, regardless of when you're sitting it. And what they'll also be looking at will be how the structure links to the properties. Okay? So that's what I'm going to try and focus on, and really try and work to get your understanding to that stage where you can actually... you understand why the properties are like they are, not just remembering what the properties are. Because that way, if you do go and you get that brain blank, you can try and think through the sort of logical steps and then work it out and put something down that's going to eat you some of the marks. Right, so as we said, we are looking at Chemistry 2. Now, the fundamentals to this, we're looking at, we're going to have ionic bonding, we're going to look at covalent, and this won't all be today. Covalent's broken into sort of two smaller groups, which is small and giant configurations. We're going to be having a look at metallic as well. In terms of keywords that we need to try and get our heads around, obviously we're going to be looking at the difference between atoms and ions. Remember, an atom, we have the same number of protons and electrons, because the charge is neutral. So we've got the same number of positive charges, the same number of negative charges. We don't ever change the number of protons, we leave that to physics. However, if we change the number of electrons, we now don't have the same number of positive and negative charges, so that becomes an ion. And particularly important when we look at ionic bonding. We're going to be having a look at words such as intramolecular. And this is generally inside a molecule. And we're going to be having a look at intermolecular. And that is going to be between molecules. If you think about the internet, international is between countries. So intermolecular is going to be between molecules. So we'll look at those. But if we can't remember it, we could just say inside a molecule or between them. But it's nice to be able to use the correct words for these. We are particularly going to be talking about energy here. And we're going to be talking about forces as well. Conductivity is going to be quite important. Melting and boiling point. And we're going to be looking at how these words link back to the forces involved, link back to the properties. Now, there's one pretty much underlying key concept, which is the sort of foundation for every type of bonding, whether it's at GCSE, whether it's at A-level, and the more you understand bonding, the more you can take everything back to this sort of key concept. And it's nothing that's new to you, but it is this idea that opposite charges attract. Okay, and that should be, oh, I can't even draw straight lines, I'm writing over my text today, but this should be in the forefront of our head, big bold letters, flashing neon lights if you can do it. Because actually, we're going to take everything back to this idea. And when we start looking at a lot of the properties involved, it's going to be the size of the charges and the way those charges interact that actually determines a lot more of the properties. Another key word, while I remember it, it's going to be delocalized. We will... What's the other one I was thinking of? I'll come back to me in a bit. So what delocalized, particularly when we're talking about electrons. So that's quite important as well. Metallic bonding, we'll look at malleable and ductile. So if you are keeping a sort of making your own sort of vocabulary list, your own sort of thesaurus dictionary of science words, these are the sort of ones you want to be listing down and trying to make sure that we've got these somewhere. It's quite a nice, if you're making revision cards early, sort of to give yourself plenty of time to practice these, actually just having revision cards with keywords on for all the different topics, but that you can shuffle up, pull out a keyword and go, actually, can I remember what that definition means? Can I put it into context? Because if you can do that, then you'll be able to do it in the exams. And if you can't, then straight away we can go back and you can have a look and look at all the different sort of resources that you've got, or come and ask one of us for help with it. But it's quite a nice thing to do. Keyword on one side, definition on the other, and then test each other, get your family to test you, or just test yourself. Right, so let's start properly with ionic bonding. Ionic bonding then, some sort of key things we need to know. Again, if we're looking at key notes, key concepts, things that are linked just to ionic bonding, we are looking at between metals and non-metals. So quite important that we've got our heads around that. We know that one because actually if it's between a metal and it's between a non-metal, it is going to be an ionic bond. So really quick way of identifying what's going on. We are going to have a look at the transfer of electrons. So again, whenever we look at ionic bonding, it is the transfer. There is no sharing involved. That is covalent. And if we have the transfer electrons, we can also say this is redox. We looked at a bit of that last time round. Redox is definitely... Morning, Olivia. Redox is definitely higher level. So if you're doing foundation, keep going with it. It's worth learning because you never know. You might get onto the higher paper. Less marks is needed on the higher paper to get the grades, but the questions are a bit more tricky. But we cover that in C1, and we're going to be looking at it again in this topic as we go through. We should also know that metals are always going to be the ones that gain talking rubbish. Metals always lose electrons to become positive ions. Okay, so metals always lose electrons to become positive ions. Likewise, non-metals gain electrons to become negative ions. I won't always write the full words out. I'll often do shorthand, but that symbol there, those of you that have had me before will realise that is shorthand for negative. So, as we move on then, so we've got that. If you've got, and I'm just making sure I definitely put it on there. Cool. Yeah. So if you go back to Google Classroom from last week, you'll notice I uploaded the cheat sheet for you, which has got all of the different groups. And we're going to go through some of this now, but it's got all of the different groups, which ones lose, which ones gains, and the charges they form. Now, ideally, you don't need to memorise that page because as we've been going through, and if you can keep on top and keep working at it, you can actually work it out in the exam. We know that group 1 has 1 electron in the outer shell, so it's going to lose 1 electron to become +1. So if we can work it out, it's less to remember. But that sort of cheat sheet, and I call it a cheat sheet because actually, if you can use the periodic table well, it is like going into the exam with half the answers. And we get given the periodic table. So the better that you can do with this, the more you're going to be able to sort of just work out in the exam, less you have to actually memorise. So, if we look at metals, these are going to be called cations. Another key word for you there. And the negative ones are going to be called anions. Okay? So, let's have a look at how this actually translates to what we're doing. Let's move up. As I just said, if you look at the cheat sheet from last time round, we know, and I'm just going to change the colour just for a minute. We know that if we've got group 1, we are always lose 1 electron, and it's going to become a +1 ion, cation. If we look at group 2, we're always going to be losing 2 electrons and become a +2 ion. And that's quite important. If we go the other way, if we look at group 7 is going to gain 1 electron, which means it's going to become a -1 anion. Now, if I know this, and if I know the groups, I can actually work out the bonding for any of the salts that we form. And I'll come back to the word salt in a moment. When we're looking at any sort of ionic reaction, I don't need to know what the element is, because it's always going to be the same, because they've always got the same number of electrons in. There may be different levels of reactivity, so some reactions might be more vigorous. We might have some slightly different properties, but actually in the way they react and the way they bond and the way we draw them out, it's always going to be the same, which is why actually learning these rules is so powerful for this. So let's start off with a really simple one. Let's start off and let's have a look at the reaction between, let's do sodium and chlorine gas. Now this is one we can do at school, and I'll show you, those of you in my class will show this at some point. You can literally get a gas jar, we can get some sodium, we can heat it up so it's glowing. In fact, I usually heat it up till it catches light, and then we drop it into a jar of chlorine, and we get this sort of flare up of sort of white gas to start with, but it's sort of the powder that's been vaporized. And then actually what we find out is that we end up with sodium chloride. And once everything's cooled down and that powder is settled in there, we end up with sodium chloride salt. And this is the same stuff that we would cook with. So let's just balance this, because I can't cope if it's not balanced. There we go. So this is the reaction that happens. We're going from a solid to a greeny coloured gas, and we should know it's a greeny coloured gas from last lesson. And we're going to form this sort of white salt that we're really familiar with because it's used in cooking on a regular basis. Notice that any ionic compound we're going to be calling salts. So when I'm using this definition, I'm not just talking about the thing you put on your chips. I'm going to be using salt as a term for any ionic compound that we can generate through an ionic reaction. And that's quite specific. Sodium chloride is just one type of salt. Most salts are going to be inedible. A lot of them are going to be toxic. So we can't just use the word salt in chemistry anyway, as something that we can eat. It's in the same way that in physics we can't use weight as something that we measure in kilograms and stones. And those of you that I've taught before will realise sort of the term Weight Watcher is scientifically incorrect. Because it's everyday language, but when you look at the science terms, it doesn't really fit in. And it's going to be the same thing here. Yes, what we put on our food is salt, but it's not the only type of salt. A salt is any form of ionic compound. Now, when we start drawing these out, we're only going to be focused on the outer electrons. And that's perfectly fine in the exams, because as I said before, we could choose any of the groups or any element in group, well, pretty much 1 to 7, with the exception of group 4, because at GCSE only, group 4 doesn't form ionic compounds, because we're never sure whether it's going to go positive or negative, because it's already got a half-filled shell. But we can choose any of those, and we can draw an ionic diagram in the same way I'm going to do this in a moment. But we know that we can only draw the electron configurations for the first 20 elements based on the information I've given you so far. So if I was to use something like iodine, iodine's not in the first 20. I think it's in period 4 or 5 from the top from memory. So we wouldn't be able to draw that, but we could still draw the diagram if we only include the outer shell. So what I'm going to be doing is I'm going to draw these. Let's just draw that one. I'm going to draw a circle for sodium. I'm going to draw another one for chlorine. And then we're going to draw the ions over this side. So I've got sodium. I've got chlorine. That's going to be my sodium ion. And that's going to be my chloride ion. I'm only drawing the atoms at the moment. I'm not drawing them in the molecule. That starts getting a bit complicated because actually the chlorine molecule, as you'll find out later, is a covalent molecule. But in the way it reacts in the same way. It's just not worth confusing matters. So, the first thing we do is we identify the groups they're in. So sodium is in group 1, and we know that's going to have 1 electron in the outer shell. Chlorine is in group 7, and I'm going to draw these as circles for the moment, just to make it a little bit clearer where the electrons are coming from. But it doesn't make any difference. So, chlorine is in group 7, so is going to have 7 electrons in the outer shell. Now we said that when we look at ionic reactions always involve the transfer of electrons. Metals always lose, non-metals always gain. So the sodium is going to lose that electron, and the chlorine is going to gain it. Now, on the other side, if we actually have a look at what's happened now, we always do these in square brackets to show it's an ion, and we put the charge on there. There's no electrons in the outer shell for sodium, so I'm going to leave this one empty. But if I have a look at the chloride ion, it's an ion, so it's in square brackets, and it's a negative charge. There is the 7 electrons for chlorine that we started with. And there's the one from the sodium. So that is now the chloride chloride ion. And the final molecule name is sodium chloride. Okay? Now, one of the things that is probably one of the most common questions for Chemistry 2 in the exams is they will ask you to describe this in words. They will often get you to do the diagram as well, but they'll get you to describe it in words. So what I'm going to be doing for a little while now is we're going to draw some of these diagrams. We're then going to write them down in words as you would do it in the exam, so you can start seeing the different examples. A lot of these questions vary between 3 and 5 marks, but realistically you only ever need to do 2 bullet points to get all of the marks for it. And those bullet points should describe the electrons that are being transferred, the number of atoms and ions involved, and what the final charges are going to be. So let me show you what I mean. So I would start off with sodium, and I would say sodium loses 1 electron to become a +1 ion. Okay, bullet point number 1. Bullet point number 2. Chlorine gains, and I'm going to say the electron, because by putting the word the in here, it indicates it's the one that sodium's lost. To become a -1 ion. So in terms of marks for the exam, what we're looking at is we're going to get marks for saying that sodium is losing. We often get marks for saying the number it loses and for the charge. And the same way for chlorine. And depending on how complex this is going to be, depends on whether this is going to be between 3 and 5 marks. And we'll have a look at some more of these as we go through. So make sure that you can identify the atoms and the electrons that are being transferred, and the final ion charges. Let's look at another example. I'm going to do several of these examples, so bear with me, but it's important to see some of the different sort of combinations and permutations that can occur, so that you don't get confused. And then what we'll do, probably look at towards the end, is I'll show you how we can talk about redox with these as well. Now, let's have a look at group 2 and group 6, because it's probably the next easiest one to do. So let's pick magnesium, and let's react it with oxygen. So magnesium oxide, and you'll see why it forms this in a moment, is MgO. And again, I'm just going to balance this out. We'll put our state symbols in. So we're going to form that. Now, if I go through and draw the outer shells again, this is exactly the same as I've done before. And let's just go through and put well, Mg, I've got O, and I've got Mg, and I've got O. So nothing particularly complicated there. I'm then going to have a look at the group. So magnesium is in group 2, so I must have 2 electrons. Oxygen is in group 6. Oh, let's see the circles, just so you can see the difference. So I've got 6 electrons in the outer shell. As we said before, magnesium is going to lose its electrons, oxygen is going to gain. In order to get a full outer shell, magnesium needs to lose 2, and lucky enough in this case, oxygen needs to gain 2. So we're going to get that happen. Now over this side, we need to show that this is an ion. So there's my square brackets. Now, remember, magnesium has lost 2 negative charges. So it's become positive twice. Because every time I remove something that's negative, I get left with something that's more positive. If we want to work out why, then we can have a look at the fact that magnesium has 12 protons. So we've got 12 positive charges, which means we would have 12 negative charges in the atom. And if we add those two together, we end up with a 0 charge. If I do the same thing over here, I've still got my 12 positive charges, because remember we can't change that. But if I've taken 2 away, I've only got 10 negative charges now. So if I add those together, my overall charge becomes +2. Okay, which is why I've got +2 up here. If we do the same thing for oxygen, let's put my electrons in. There's the 6 it started with, but remember it's gained 2 from magnesium. So if I do the same thing, oxygen is 8, so therefore I'm going to have 8 protons. No, it's not. Yes, it is. So I'm going to have +8. But I've gained 2, so it's now going to have 10 negatives. So if I add those together, I end up with -2. So that's my charge. So if you remember last lesson, we said when we're naming these, when we take any of the sort of non-metals and turn them into an ion, they end in IDE. So this goes from oxygen to oxide. And that's going to be my anion. Tanishka. Yes, so any atom becomes an ion when it becomes charged. So if it loses or gains electrons, it goes from an atom to an ion. So we've always got atoms over this side, and I've got ions over this side, because we've had a transfer of electrons that makes them charged. Does that help? Now, let's have a look at what we would write if we were putting this into words. So, I'm going to start off with my metal, and I'm going to explain what's going on. Magnesium, remember that's my atom, loses 2 electrons to become a +2 ion. Oxygen gains 2 electrons, and I would probably put the 2 electrons, or I could just put the electrons, to become a -2 ion. And I could put down, if I wanted to, magnesium loses 2 electrons to oxygen, or oxygen gains the 2 electrons from magnesium. That's not a problem at all. It's not going to get any extra marks there, but if it makes you happier because you understand more about what you're putting down, that's not a problem at all. So this should be fairly similar to what we did with group 1. Let's just choose another one in the same context, and then I'll show you a couple of more slightly harder ones. Although if you've got your head around this, you probably won't find them that much harder. So let's have a look at group 3 and group 5, because they're done in a similar way. So let's choose aluminium, and let's just react it with, let's just go for nitrogen. We're going to form aluminium nitride. Okay. And again, we'll just balance this. So, aluminium, nitrogen, aluminium, nitrogen. Group 3, 3 electrons. Group 5. Let's do it that way. 5 electrons. Generally, in fact, I'm not going to do it that way. Doesn't make a difference. You wouldn't lose any marks. From a chemist's point of view, that's slightly better. But I'll go through why that is another time. I've done this as crosses again. Again, I can do them as circles. Doesn't make any difference. So, let's have a quick look. The aluminium is going to lose 3 electrons to get to a full outer shell. So, let's draw the ions. Aluminium has lost all of the electrons in the outer shell. It's lost 3 negative charges, so it's going to become positive by 3. If you want another way of doing it, I will let you do the same calculations I did a minute ago. Look at the periodic table, work out the number of protons, and do the calculations I just did for group 2 and group 6. Nitrogen, let's just move this over a little bit. Nitrogen now should have a full outer shell because it started off with 5, it's gained 3, which means it's now got 8. And we've ended up with that. If we want to draw this out, let's do, write this out. And I'll write it slightly differently this time. Aluminium loses 3 electrons to nitrogen. To become a +3, I'm going to go with cation. You put another key word in there. I'm not going to get any extra marks for this one. I'm just showing you some different ways of doing it, and we can start bringing in a few more keywords here. So, nitrogen gains the 3 electrons to become a -3 nitride anion. So if you want to try and use some of those words, it's good practice. It won't get you any more marks in this one unless the exam questions specifically ask for it. But it's really good to practice using these words to see if you can use them in context. Now, let's have a look at a more complicated example. Because on the higher paper, realistically, this is where we're going to start heading to. This is where we're going to start getting higher marks for. And there's not that many of these examples that they can actually ask you to do. I'm going to show you probably 3 more. And if you have any questions as we're going through this, just let me know. Right, let's start off with magnesium. Let's start off with magnesium and chlorine gas. So when we do this, what we should end up with is this salt. This is magnesium chloride. Okay? Notice it's got a different formula. When we looked at sodium chloride, it was NaCl. This is now MgCl2. And one of the skills that you need to be able to learn and properly get your heads around is to be able to work out the final formula of any salt that you're given. And I'll show you a few different ways of doing that. Realistically, hopefully, as you go through and by practicing some of these, it should start to click and make sense over time. It's one of those that you need to keep coming back to though. So I'm going to do exactly the same as I did before. I'm going to start off by drawing 4 circles. And we'll see what happens as we go through. Now, magnesium, chlorine, magnesium, and that's going to be my chloride. If it helps, I can put my square brackets in now, because remember, that's going to be my ions, anion and cation. So magnesium's in group 2, so let's put my 2 electrons in. Chlorine's in group 7, so let's put my 7 electrons in. Now this is where the problem starts, because magnesium needs to lose 2 electrons. Chlorine only has space for 1 more. Now, generally what I'll do is if I'm doing this in class, I will leave this as a problem for students to try and get their heads around. And there's lots of sort of weird and wonderful ideas people come up with, but generally we need something that's fairly straightforward. So if 1 chlorine can only take 1 electron, then we need to have 2 chlorines. So let me put another chlorine in, because that second chlorine is going to take that second electron. Now, remember, magnesium has lost 2 electrons, so it's going to become positive 2. Let's go back to black, just to try and keep things consistent. So it's going to become positive 2. Each chlorine now has a full outer shell. And each one has a -1 charge. But there are 2 of them. So my final formula is MgCl2. So this should match up to the final charge up here. The other thing that we can have a look at is if we know that magnesium is in group 1, so has a +2 charge. If we know that chlorine is in group 7, so has a -1 charge. If I add those together, my final figure at this moment in time is +1, and it's got to be 0. My final molecule has to be neutral, so I would need 2 of those to turn that to get to 0. So all of these should add up to give us the same formula for the final molecule, and we're going to get lots of practice as we go through this, not just in chemistry 2, but as we look in some of the later lessons as well. So there's a lot of overlap, and there's a lot of opportunity to repeat these topics. But you can practice this by choosing pretty much any atom out of group 1, 2 and 3, and any atom out of groups 5, 6 and 7, and work out what the formula of the salt is going to be. So let's have a look at how we would actually write this if the question was asking. So we're going to say magnesium loses 2 electrons to become a +2 ion. Now this isn't the only way of doing it. I could turn around and say magnesium loses 2 electrons to 2 chlorines, or that gets a little bit more confusing, but we could do it that way. I'm then going to turn around and say 2 chlorine atoms each gain 1 electron to become -1 ions. Okay? So I've made it really clear what's going on. Yeah, Tanisha, absolutely right. If you're not given the name of the product, you do need to be able to name them as well. So, for instance, we could actually, they could say what would be produced if we reacted this metal and this non-metal together. And we're going to come on and we'll do more naming as we sort of work our way through. Naming of chemicals is an international convention, and it doesn't matter where in the world you do chemistry. You should be able to be given any chemical name and work out the formula for it. So all of this ties in and sort of adds up to the more you understand here, the less you actually need to know. So let's look at another example, and we'll see how we can use similar sort of ideas for this. So last time I looked at group 2 and group 2 and group 7. Let's have a look at group 1 and group 6. So I'm going to choose sodium and oxygen. So we're going to react sodium, metal, with oxygen gas. And as you'll see in a minute why, that's going to form sodium oxide solid. That's a really big G there. Never mind. I need to balance this. And as I said before, I'm going to do balancing as a separate topic. I'm not going to go into how it all works now. I'll probably look at doing that when we look at doing quantitative chemistry a little bit later on. So that's balanced here. And we need to work out why it is that sodium formula is Na2O. So this should hopefully be getting really boring in terms of I've done this before. Why is he going through the same thing again? And actually, it is the same thing over and over again. But this is higher level work. And actually, if you can do this, we can get a lot of marks really, really quickly. And the idea that I want it to be so, I suppose, routine for you that you don't have to think about it anymore. So it is that dull. And if it's getting to that stage, brilliant. If it's not, keep working at it. So, sodium is in group 1. 1 electron. Oxygen is in group 6. Let's go back to circles just for a change. Now, if we do what we've done before, sodium needs to lose that 1 electron. But I've got a problem. Oxygen needs to gain 2, but sodium can only get rid of 1. So the easiest option is to put another sodium in. Okay, and that then should start looking a little bit like the formula that I've got up here. Let's put our brackets in to show these are ions. Each sodium is losing 1 electron, so it's a +1 charge, but I've got 2 of them. And remember the oxygen, it's going to do that, and it's going to be a -2 charge. So that should match perfectly the formula up here. And if we want to write this as words, then sodium will lose, in fact no, I'm going to change that, I'm going to put 2 sodiums. Two sodiums, and don't be afraid to annotate and change your work in the exams. It's part and parcel. Personally, I think the worst thing that we can ever see is a really, really neat exercise book with no mistakes in, because it means you're not learning anything and we're not having to go through and redraft our work. It's perfectly normal to be able to do this. And if you go and see the work of any academic, pretty much anywhere in the world, apart from their final dissertation, which ends up, or their final sort of documents, which might end up in a book, their work will be absolutely all over the place. And those of you that I teach will know I've had this conversation with it before. You know who I'm talking about. You don't want to sit there and have really neat work. You want to be redrafting. You want to be sort of brainstorming and doing things. And if you look at the notes I made before I started teaching some of these lessons, which is why I keep looking over this side, it's pretty much the way I teach normally. There's bits going everywhere as I change, because it shows my thought process. So don't be afraid of redrafting. It doesn't mean you've made a catastrophic mistake. Okay? So 2 sodiums will lose 1 electron each. I'm sure some people think it's a slight on themselves if they've made a mistake, rather than the fact it's actually normal and it's a really good thing. So 2 sodiums will lose 1 electron each to become +1 ions. And I bet there's a couple of you there now that are sat there grinning because you know exactly what I'm talking about. Oxygen will gain the 2 electrons. To become a -2 ion. Yeah, it's exactly the same format. I haven't changed anything. It's still 2 bullet points, but there's a lot of information going in here for the exams. We've got the number of atoms, we've got the charges, we've got the number of electrons, we've got where the electron's going, but I'm still only using 2 bullet points. If we're having to write paragraphs and paragraphs to get the marks on these, we're doing something wrong. It annoys some people, but we know when we're looking at English want descriptive. They want lots of information. They want our sentences to be structured perfectly. Scientists aren't like that. We want the maximum amount of information in the fewest number of words. And it's a real skill to learn. In just the same way as descriptive writing in English is, you need to practice getting as much information across without having to write lots. As a scientist, I don't want to see huge amounts of descriptive text. What I want to know is just the facts. That's all I'm interested in. And when I'm scanning through people's work, most of the time I'm ignoring everything you've written and just looking for what facts have you included. And that's what we're trying to achieve here. Right, 2 more. I'm not sure if that's a groan because there's 2 more, or a slight cheer that there's only 2 more left. Right, we're going to have a look at aluminium, and we're going to react that with chlorine. So, our formula for this, and if you're coming through and you're looking at this and you're not doing this live, feel free to pause it and try and work it out. But it's going to be AlCl3. Now, in order to balance this one, I'm going to need 2 of those, and I'm going to need 3 of those. If you know how to do that, brilliant, but again, we'll come back to this later on. We're going to do the same as we've done before. I'm going to start off with my 4 outer orbits, 2 atoms, 2 ions. And I'm going to put my square brackets in first this time. So, aluminium, chlorine, aluminium, chlorine. Group 3. Group 7. Notice, as I said when we looked at chemistry 1, I'm pairing up these electrons. That's partly because that's actually what happens, and that's partly because it makes it so much easier to work out. I can look at that straight away. I've got 7. If I try and spread them all the way around, you're not going to lose marks, but you end up with a lot more miscalculations on this one and a lot more opportunity for mistakes. So, aluminium can only lose, sorry, it needs to lose 3, but it can only give 1 to chlorine, because chlorine only has space for 1 before it gets to a full outer shell. Oh, let's just move that up. Get rid of that one. Let's put that back in again. There we go. No, it's filled it in. Much better. So. Now, we can put one of them in there, and I can put one of them in there. And if you notice what the formula for it is, up here, sorry, I'm pointing to it, it does help if I actually do it on the screen, AlCl3, AlCl3. So when we look at the electrons prove that is the correct formula for this one. My aluminium has lost all the electrons in the outer shell. It's lost 3 negative charges, so my charge is +3 or 3+. It makes no difference which way around you do that. If we look at the chloride, we know that each chloride has a full outer shell. Each one has gained 1 electron, so it's going to become negative by 1. And there's 3 of them. And if we want to write this out, aluminium loses 3 electrons to 3 chlorine atoms to become +3. Now, I may want to clarify this a little bit more to say that it's 1 each. What I'm going to say is 3 chlorine atoms each gain 1 electron to become a -1 ion. So I've still only done 2 bullet points. I didn't mention any names with the books. Right. So hopefully that makes sense. And to be fair, it's not just you. There's several others in lots of different classes. But it did make me chuckle because you guys know exactly what I'll be talking about. Brilliant. So the last one I want to do is pretty much the hardest one that they can ask you at GCSE. Because there's only so many combinations that you can do. And that would be a combination of group 2 with group 5. Or group 3 with group 6. And it doesn't make any difference which way round you do that. But that particular combination of charges and electrons is about as hard as it can get at GCSE. So let's just have a look at what this would look like. So I'm going to go with aluminium and oxygen. Now, I'm not going to do the final molecule for the minute because we're going to work this out by drawing these in. So, start in exactly the same way. There we go. So we've got group 3, group 6, and I've got my ions. The format, the routine that I actually go through when I'm doing these, none of this has changed, okay? We're going through exactly the same thing. It should be really dull. Yeah, we're doing lots of this. We can put arrows in here if we want to, because this is exactly what's going on. Now let's see what's going to happen. So aluminium needs to lose 3. So straight away, I've filled the oxygen, but I've got 1 electron left. So in the same way as we've done before, I'm going to need another oxygen. So let's put another oxygen in here. Now, that electron goes in there, but this electron doesn't have a full outer shell yet. So I'm going to keep things simple. I need another electron, so I'm going to draw another aluminium molecule. Let me draw another aluminium molecule in here. Brilliant, so that oxygen's filled, but I've got 2 electrons left. So, same again. Those 2 go in there. That one is now filled. So if I then translate this across to the other side and draw the ions, each aluminium has lost 3 electrons, which means it's become positive by 3, and I've got 2 of them. Each oxygen, let's just draw these in, has gained 2 electrons, 2 negative charges, so it's become a -2 charge, and I've got 3 of them. So my final formula up here for aluminium oxide is Al2O3. If we look at the charges, aluminium's +3. So oxygen is -2. I need to get to a 0 charge. So if I multiply that one by 2, I get to +6. If I multiply that one by 3, I get to -6. My overall charge is 0. So that's about as complicated as it gets. As I've done with all of the others, I'm going to show this to you in words, just so we can see what's going on here. So let's write this out as if it was an exam question. So what would I write down? Let's go for 2 aluminium atoms lose 6 electrons to 3 oxygen atoms. I'm going to put another bullet point in here for the moment because I want to be really clear what's going on. Now, we can do it in 2 bullet points, but I don't want to confuse things. And actually, this is a more complicated one. This is probably going to be a 4 or 5 marker, probably 5 marks in the exam. So I'm not worried about putting another bullet point in here. 2 aluminium atoms lose 6 electrons to 3 oxygen atoms. I'm going to say that each aluminium atom becomes a +3 cation. I'm then going to turn around and say 3 oxygen atoms gain 2 electrons each to become -2 ions. So there's a lot of information in in relatively few words. But actually, when you think that's worth 5 marks in the exam, that's really nice because we can gain marks so fast on these. And the grade boundaries on chemistry traditionally are quite low because students struggle to get the marks on things like this. So the more practice you get, and realistically, as I said, you can choose any atom, even if it's an experiment, even if it's the radioactive ones. So if we're looking at francium, it doesn't matter in terms of practice, whether it's a reaction we would do, whether it's a reaction that's probably going to work in real life. This is all about practicing. Can we transfer electrons from one atom to another? Can we work out what the ions are going to form? And can we work out the final formula of the salt? And can we do these 2 or 3 bullet points to describe in words what's happening during that chemical reaction? Now, what I just want to talk about, and I'm going to just briefly talk about the properties of ionic compounds, and then I'm also going to start next lesson with this one. So we've obviously only looking in our terms of what we're writing about 1 or 2 atoms at a time, but realistically this is going to happen on a huge scale. We know this term moles, and moles is going to come in C3 properly. When we're talking about moles, we're talking about huge numbers of atoms. Okay, so we're looking at 6.02 times 10 to the 23 if we had 1 mole. And a 1 mole of, say, sodium would be 23 grams. So it doesn't make any difference with these. 23 grams? Brain's fried today, can't think off the top of my head. Something like that. Magnesium is 24 grams for 1 mole. But we might be talking about kilograms of the stuff. So we're talking about huge, huge numbers of atoms. Okay, so these electrons transfer, and what we end up with is lots and lots of positively charged ions, lots and lots of negatively charged ions. And if you can remember, if we actually had a load of magnets and we threw them all into a box, they're all going to clump together and they're going to form this solid. And that's what's happening here. So if I was to this reaction to happen, what I'm going to end up with is a sort of 3-dimensional molecule. I'm only going to draw it as 2-dimensional for the moment. Very similar to, it's very badly drawn, I'll get a better diagram for you next time round. Very similar to what we would draw at key stage 3. There's my positive cations, And we're going to have our negative anions alternating through that. So what I've ended up with is all of these are going to be clumped together, and we've got these strong ionic bonds. These are intramolecular forces. Because whenever we look at, so if you look at a salt crystal, that's going to be one molecule. It's a huge molecule, but it's one molecule. So we've got these strong intramolecular ionic bonds or forces, however you want to call it, because these are caused by these opposite charges attracting. Now, in the same way as it's quite difficult to start pulling magnets apart, it's actually quite difficult to separate these. So if you wanted to melt it, if you want to turn it from a solid into a liquid, you've got to give those particles enough energy to start vibrating fast enough that they can actually start breaking these bonds. Now, the link between temperature and the kinetic energy of the atoms we call kinetic theory. And I'll talk about this, I think, a little bit more on Wednesday. But what we're trying to do, in order to melt these, we've got to give these particles enough energy to break those forces between them. So we're going to end up with high melting and boiling points. High melting and boiling points because we've got strong intermolecular forces, which means lots of energy needed to break. Okay. Now, I'm going to leave that there. I just want to sort of throw that in to sort of finish, or to start next time as we finished here. What I want you guys to do over the next sort of day or two is go back over these notes. I'm going to drop all these notes as usual into Google Classroom. If I just zoom out so we can sort of have a quick look at what we've done. Remember, use the periodic table. Work out what the charges the ions are going to be formed. Have a go at doing these diagrams for some random ones. If you want to take a picture of those and then email them through to me as examples and for me to check, that's absolutely fine. I don't mind doing that. I'll reply to you. But practice doing these. Any group 1, 2 or 3 metal with any group 5, 6 or 7 non-metal. What's the formula of the salt going to be? What are the formula of the ions? And then have a go at writing it in words as well. But you need to be able to do these diagrams and these words for any of those. Okay? Right. Have a great day. I look forward to seeing some of you soon, hopefully. Take care. Hope that was useful. Bye-bye.